Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. So for me as a student in Jerusalem, in the Hebrew University, I often heard about profit inequalities that were very popular among the statisticians there. So it's great to see them occur now in this topic. So Balu Sivan will tell us about revenue maximization and profit inequalities.
Yeah, thanks, Yuval. So this is based on a couple of joint works and a bunch of other work that has been going on in the past 6 years on this multi-parameter revenue maximization, and I'll acknowledge these as I talk about them. Okay. So what's the setting? It's a very simple setting. You have n agents, m items, and each agent has some value for item. Valuation of agent I for item j is Vij, and this valuation is of course private knowledge. Only the agent knows his value for the item, and these valuations are drawn from distributions which are public. Everybody knows about these distributions, and the assumption throughout the talk is that these Vij's are all independent. Okay. So for this talk, I'm going to focus on unit demand agents. Unit demand agents are those who are interested in buying at most one item, which means even if you give them a whole bundle or set S, their valuation is basically the most valued item in that set S. Okay. So what you want, your goal is to maximize revenue by doing some matching between these agents and items, right? It should be a matching. You should not give any agent more than one item, and no item should be given to more than one agent. Okay. So this.
What's the setting we should think of where unit demand is involved?
So for example, while you go shopping for a hotel, for example, you don't want more than one hotel. So, okay. So this is a multi-parameter revenue maximization problem. Multi-parameter because each agent has more than one private parameter. Okay. He has value for each item. So he holds m private parameters. Everybody holds m private parameters. Okay. So formally, we are studying a multi-item auction problem. You have n unit demand agents, m items, and you have a matrix F of distributions. Your goal is to get a seller optimal auction. Okay. So what is known? What's known about this? So it's very well understood how to design revenue optimal auctions in single parameter settings. Okay. For example, if you set m equals 1 when there's just one item, you know what to do to get the revenue optimal auction. And in Meyerson's work, what he basically shows is that you can reduce revenue maximization to welfare maximization. Okay. If you transform values to what is called virtual values, which is a distribution dependent transformation of values, after that on virtual values you just run the Vickrey auction or the VCG auction, and that will maximize revenue. That's what he said for single parameter settings. But this completely fails to extend for multi-parameter settings. Okay. In particular, you get some nice insights there from Meyerson's mechanism, for example, that the optimal mechanism is always deterministic. Okay. And such kinds of things fail to extend to multi-parameter settings. And even in single parameter settings, it's very rarely used, Meyerson's mechanism. Okay. So, the obvious question is, can we get some sort of structural understanding for multi-parameter settings also?
So just to understand, were you assuming the sellers are IID, or are you doing
There is no seller here. There's one seller. I mean, no, not IID. So the distributions could be different for different items, agents, and everything. It's just independent.
So what do you mean by parameter? Parameter would be the
parameter is the private parameter, all the Vij's, right? Each agent agent I has Vi1, Vi2 till Vim. So it's more than one. Okay. So if you just, when m is equal to 1, he holds only one private parameter, and in those cases you know how to maximize revenue. Okay. Yeah, so it would be nice if you can get some sort of understanding of how optimal mechanisms look like in multi-parameter settings. So in Vincent and Manelli, what they say is that you can't do this. Basically what they show is that even for independent distributions, the class of all optimal mechanisms is basically includes almost all possible mechanisms, so you can't get any nice characterization of optimal mechanisms. So one of the takeaways of this talk is that you can get some nice guidelines about how near optimal mechanisms look like, okay, if you're willing to relax optimality and look at approximately optimal mechanisms. Okay. So what we show is that very simple posted price mechanisms, which are not like normal auctions, traditional auctions, which ask people to bid and then decide whom to get allocated, whom to allocate, and then what they pay. Instead, you just put prices on items, and agents come and choose, whether they want to take it or not. It's a take it or leave it offer. Simple posted price mechanisms are actually approximately optimal in multi-parameter settings. They're good in single-dimensional settings, and they extend to multi-dimensional settings. Okay, and they're also widely used, of course. Everywhere you just see prices in most of these settings.
What do you mean by dimension? Is it same?
Single dimension is same as single parameter. Yeah, multi-dimension is multi-parameter. Okay. Okay. So this is the outline of the talk. Okay. The main tool is basically understanding these multi-parameter preferences. These are complex objects, and that's why it was difficult to find out how much you can extract optimally in the settings. So we are going to reduce this multi-parameter problems to a single parameter problem. That's the first step. Then the goal is to develop good posted price mechanisms for single parameter settings, and that's where I'll make the connection to profit inequalities, and then show that these mechanisms can also be generalized to multi-parameter settings. Okay. Now, assumption throughout the talk, as I already said, is this F is a product distribution. Okay. For simplicity, for the first part of the talk, I'm going to focus on single agent settings, which means that there's just Vi here. The second index is dropped. There's only one agent, right? So you can think of V1 to Vm, and these are all mutually independent. I'll briefly talk about correlated values towards the end of the talk. Okay. So this is a single agent setting, right? There's one agent and these m items, and you want to construct a revenue optimal or near optimal mechanism in the setting. So how do you understand this multi-parameter preferences? We'll use the approach developed by Shuchi Chawla, Jason Hartline, and Bobby Kleinberg in 2007. So what they say is that you don't understand this, but you can construct a related single parameter setting, which we do understand well, and this is the related single parameter setting. So when you have one agent, it's 4 items, think of this or break this agent into 4 representatives. Okay. Now each representative is interested in buying exactly one item. Okay. So this multi-parameter agent is broken into 4 single parameter agents. Okay. There's only one private value that agent is hiding, and you now retain the same feasibility constraint as in the original setting. Okay. In the original setting, the feasibility constraint was that he's a unit demand agent. You can give him at most one item. Right? Feasibility. What's the feasibility constraint? It's basically some set system over the edges, right? Over agent item pairs. You maintain the same feasibility constraint here. Here you say that at most one item can be allocated. Okay. And so we are basically in a single item auction problem in m agents and one item. One agent m items has been transformed to m agents and one item. Okay, so this is the rated single parameter setting. Okay, so what about this setting? So the claim is that the optimal revenue in this new single parameter setting is at least as much as the optimal revenue in the original multi-parameter setting. Okay, and what is the intuition? Basically, the single parameter settings, these representatives are going to compete with each other, right? They act independently. Whereas in the original setting, the agent made a joint decision for all the items, right? He'll pick the item which maximizes his utility. Here, these representatives are not going to say that, oh, that guy has a higher utility, so I'll leave this item for him, right? So you can use the competition to get more revenue. That's the intuition, and that can be formalized. But I'm going to caution you that this upper bound holds only for deterministic mechanisms. Surprisingly, it fails for randomized mechanisms, although it holds for constant factor, and that's something I'll get to towards the end of the talk. Okay. But if you take deterministic multi-parameter mechanisms, then their revenue is upper bounded by this related single parameter setting. Okay. So that's what they say. Okay, but so what, right? I mean, you have this single parameter setting. You know how to construct the optimal mechanism in the single parameter setting, Marston's mechanism. But what to do with it, right? You need something to apply to the multi-parameter setting, and you don't know how to use this Marston's mechanism. What's the main challenge here? Which is basically to eliminate competition, right? In this single parameter setting, there is competition. In the original setting, there's no competition. This guy is looking for his best interest while choosing between items. So if you can design a mechanism, so what is competition basically? If there is competition, there is room for collusion. Agents can say that the seller is using competition to extract revenue from us, so people can collude and bring down your revenue. So if you can design a mechanism which is robust to collusion, its revenue doesn't go down by collusion, then you can use the same mechanism in the multi-parameter setting. Roughly, that's the kind of mechanism you're looking for. So traditional direct revelation mechanism where you submit the bids and then you do something that's always subject to collusion, like Meyerson's or Vickrey's second price auction, etc., are all subject to collusion. So that's what we need, like collusion resistant single parameter mechanisms which can be applied to multi-parameter settings. And the candidate we pick is the posted price mechanism in single parameter settings. So you have, think of a one item auction, you have n agents. Instead of asking for bids or anything, just say that I have a price pi for agent I, okay. And then agents would come in any order, and agent I comes, he faces a price pi, and if the item has already not been sold, he can choose to buy it at that price. If his value is higher than p, he's a rational agent, he'll buy it, that's it, okay. So we are going to count our revenue as the revenue you get in the worst possible ordering, okay. So if you have agent 1 and agent 2 and these prices, if agent 1 comes first, then he'll of course pick the item, you'll get revenue 4. If 2 comes first, you'll get revenue 3. And I'm going to count the revenue from the worst ordering, and that's precisely why this is collusion robust, right. So what does collusion mean? So here, agent 2 can tell agent 1, look, I'm getting utility of 3, you get utility of 1. So if I go first, I'll pick the item, okay, and I'll split it into half and half. So you'll get 1.5, I'll get 1.5. But if you go first, you get a total utility of 1. So we are both better off if I go first, right? That is the collusion here. So what does, if people collude, what does it amount to? It basically amounts to people coming in a different order, right? Agent 2 is coming ahead of agent 1. But we are counting our revenue from the worst ordering possible, okay? So basically that's why it's collusion robust. So if we can design a posted price mechanism which is collusion robust in this sense, you can approximate the optimal revenue from the worst ordering, then you can use it to the original multi-parameter setting, right? So obviously it extends to multi-parameters, that's what I'm saying now. So if you put these very same prices in the original setting, that agent will pick the item which maximizes Vi minus Pi. Obviously this is better than getting the worst possible orderings Pi, right, in the single parameter setting. So what I just said is that if you can get an alpha approx single parameter posted prices, that basically implies the alpha approx multi-parameter posted price mechanism. So the question is, do posted price mechanisms perform well in single parameter settings, right? Okay. So to do this, I will give a quick 2-slide overview or characterization of truthful payments in single parameter settings, okay, what they look like. So if you're designing any truthful mechanism, for any truthful mechanism single parameter settings, so I'm going to talk about Bayesian incentive compatibility, but it's essentially same as the ordinary truthfulness. Bayesian incentive compatibility means that you're truthful in expectation over other people's valuations, but it doesn't matter, you just drop the expectations in, that's incentive compatibility. So what are the requirements for a mechanism to be truthful? It just says that the expected allocation function should be monotone, okay, which means that if the probability of me getting the item, okay, over other people's valuations is something now, and if I increase my value, then the probability of me getting the item should not fall below, okay. It is no smaller, and the payment should satisfy this formula. It might look weird, but it has a nice interpretation. If you draw the allocation curve, the area to the left of the curve is the payments, okay. So whatever be the mechanism, whether it is posted price or direct revelation or whatever, if you're developing a truthful mechanism, then these two conditions have to be satisfied, okay. This is a characterization. So this sort of interpretation is nice for prices, but it doesn't guide me how to design the optimal mechanism through this, okay. From this, the revenue is basically sum of the prices, right? So you want to maximize revenue, and that's precisely what Myerson did. He basically expanded the expectation, switched the order of integrals, and got an integral which is some clean thing which is dependent only on the value and a function of value, okay. And you call this function of value as some function virtual value, and this integral is basically expected virtual value, right? It's expected virtual surplus. So this is directly telling you how to maximize revenue. If the expected payment is equal to expected virtual value, you basically should give the item to the person with the highest virtual value, right? You set xi equals 1 for the agent with the highest virtual value, and that's what is Myerson's mechanism, right? So this
I once went to a play called the 3-minute Shakespeare, so this is the 3-minute Hamlet, so this is the 3-minute Myerson.
Yeah. So what this basically says is you get the values, apply virtual valuation function, you get virtual values for these n agents, then run Vickers auction, okay. That's what this is saying. Only thing is that these virtual values could sometimes be negative, okay. So if everybody is negative, you don't basically serve anybody. Vickers auction will always serve somebody. This need not always serve somebody. Okay.
There is an assumption that the virtual values are monotone.
Yes, otherwise you can do and, yeah, but yeah. Okay. So that's enough for me to talk about performance of posted price mechanisms in arbitrary orderings, right? What I wanted to do initially was that agents could come in any order, and I want the worst case revenue over orderings. I fix the prices beforehand, and agents could come in worst order, and I want to say that that revenue approximates the optimal revenue. Okay. So based on this characterization that the revenue or the payment is basically virtual values, I can think of agents coming as virtual values coming to me. Okay. When an agent comes, basically a virtual value is coming, and saying that I'm going to serve this agent is basically picking that virtual value, right? So you have these random variables or virtual values arriving to you in an arbitrary sequence, and your goal is to pick the near maximum xi. Okay. You don't control the sequence, but you can control who gets picked. So that's exactly the setting in profit inequalities. Okay. In profit inequalities, you have n random variables, and these are drawn independently from some distribution fi for a random variable I, and the profit, he knows all the random variables ahead of time, and therefore his revenue is always max over I of all these random variables, and he gets this expectation. And if you're a gambler, you don't know what's going to happen the next day, and you have to pick or drop something today. If you drop it, you can't come back to it. If you pick it, you stop, you don't see the next day. Then can you compete with the gamblers of the profits revenue? Okay, that's the profit inequality question. And Samuel Kahn had this beautiful result in '84 where she said that you just set a single threshold, okay, not different threshold, just one threshold, which is the median of the distribution of max over xi, and then pick the first random variable which exceeds the threshold. Okay. If you do that, then your expected profit is at least half of the expected max value, which is what the profit gets. So you get half of the profit by this single threshold. Okay. So this directly translates to our setting because of the interpretation through virtual values. Okay. So what exactly is happening? You have these virtual values coming to you, and I'm going to put a threshold on virtual values. Okay. It's a single threshold on virtual values. I'll pick the first virtual value which exceeds that threshold. Okay. So what does it mean to put threshold on virtual values? It basically means that you put a threshold on values by inverting this, right? But you invert different people according to their specific virtual value function, so you invert differently for different people. So there are different prices for different people, and this is the threshold on values. Obviously that translates to an agent picking or dropping, right? An agent looks at the price, and if his value is above the price, he'll pick the item, otherwise he'll not pick the item. Okay. So if you use the median of max over I of virtual values, then you get half of the optimal revenue. Okay. That's a simple connection to profit inequalities, and these mechanisms, of course, since they do well in single parameter settings by the earlier argument, they also do well in multi-parameter settings. Okay. So this is the half approximate. This is joint work with Shuchi Chawla, Jason Hartline, and David Malek. Okay. So what was crucial here, I'm saying this because I'll come to this later, that the profits threshold, the threshold you use is non-adaptive. Okay. If you keep on adapting the threshold for each item based on what happened before, then that is unacceptable for us. Why? Okay. For single parameter settings it is okay, because what it essentially means is that I will change the price for agent 2 based on how agent 1 reacted. But for multi-parameter settings where there is one agent and n items, it's not acceptable, because that's like saying that I will not tell you what the price for item 2 is. Here is item 1. You pick it at this price or drop it if you want, but later based on how you react, I will tell the price for item 2. Right? That's completely unreasonable, because you can't reason about what the agent will do. He's completely in the dark about the future prices. Okay. So you want non-adaptive prices. You can do non-adaptive prices for single agent and k items, but for more general combinatorial feasibility constraints, you don't have this non-adaptive thresholds. Okay. So what's the extension to multi-agent settings is basically very similar to single agent settings. You have these n agents, and there we broke each agent into copies. Similarly here also the single agent was broken into copies. Here you break each agent into copies. Maintain the same feasibility constraints. Okay. If some subset of edges was feasible, the same subset of edges is feasible here. The same argument will basically go through that more competition implies more revenue single parameter settings, although you need to be slightly careful. It's not as straightforward as single agent settings. Again, this fails for randomized mechanisms, which I'll come to later. The other thing I said was that you can use the single parameter mechanism and it generalizes to multi-parameter settings, and that happens here also, except that instead of putting price for this one agent, you need a price menu for each agent. You need a price Pij, which is price given to agent I for item j. You have these n times m prices. And how am I measuring revenue? Agents can come in arbitrary order, and when agent I comes, his menu is given to him, and he picks his favorite item at these prices, and next agent comes. Okay, so if agent 1 comes first, his value for item 1 and item 2 are 5 and 10, and these are the prices. He'll obviously pick item 2, which gets a utility of 10 minus 6, 4 for him. And the first one gets only 2, so he'll pick item 2, which automatically means that only item 1 is available for agent 2. Okay. And if agent 2 comes first, it gets reversed, and you get much lesser revenue. You get only 4, but we count only that as the revenue, okay, or the worst possible ordering. And again, you can look at the single parameter setting. The only thing is the feasibility constraints in single parameter setting has now become more complicated. Earlier it was just one item auction. Now you can have partition matroids and more general things. So what do we get for these general single parameter settings with all these constraints? For k unit auctions, we got a factor of 2. There's been a lot of work after hours. For example, this factor 2 is basically coming from profit inequalities, right? For single item it was 2, for k also it will be 2. And Saeed Alay showed that in a very nice paper. He showed that you can get arbitrarily close to 1 for k item auctions if k goes to infinity. Okay. And for the matching problem, which I showed on the first slide, you can get single parameter, which is 5.83 for those constraints. And for general matroids, we got order of log rank of the matroid. This was later again improved by Kleinberg and Weinberg, because they have an improved profit inequalities for matroidal settings. Although the point to note about it is it's adaptive prices. Then you can ask, how does adaptive prices work? I just said that adaptive is a problem. The beauty of that thing is there are multiple agents. The price for agent 2 can depend on price for agent 1, but within an agent the price is not adaptive. So the whole menu is presented to him without being adaptive, so they can argue about incentive compatibility, etc. But it is still open whether you can give a profit inequalities for matroids which is not adaptive. Okay, you don't change. You can put multiple thresholds, but it is not adaptive. You set thresholds once and for all. And you can't do well with posted price mechanisms if you go beyond matroidal settings. That also we show. Okay, so that's the story basically for deterministic mechanisms. You have this.
What will be the profit? What's the profit?
So okay, the problem is basically that the gambler is going and seeing n random variables, and the set of all random variables he can pick should be some independent set in a matroid. Okay, right. The setting I presented earlier is one uniform matroid, right? And this is a k uniform matroid, and this guy is saying that you will get arbitrarily close to 1 in a k uniform matroid. The other natural question is,
It's not by a different profit inequality, or same.
it is the same better analysis. That's all.
The same profit equal, just setting a single price for threshold for
Yes.
values?
And you're comparing against.
You are comparing against the gambler profit who knows all these things, and he'll pick the top. Yes. 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 Yeah, exactly. Okay. So the other thing is here the profits, the gambler's profit was getting arbitrarily close to 1. The approximation factor was getting arbitrarily close to 1. Can you get the same thing here in terms of the rank? Okay, if the rank increases. In general, obviously you can't do it, because I can create a big partition matroid which is a union of many uniform matroids, and these uniform matroids might have small. But can you put some nice restrictions on matroids and then say that for these matroids the profit you get gets arbitrarily close to gambler's profit as the rank increases? Okay, so that's another open question for matroids. Profit, yes. So the approximation factor gets arbitrarily close to 1. Okay. Okay, so for the rest of the talk, I'm going to talk about what else can you do. Okay, so where else can you go? Can you generalize to randomized mechanisms? What happens to this argument where it breaks? What happens if you go beyond independence? And what happens if you go beyond unit demand settings? Okay, so all these things were essential for our proof. Okay, unit demand settings, independence, okay, and deterministic mechanisms. Okay. Okay. So does randomization help? Okay, that's the first question. In single parameter settings, it doesn't. Okay, so it's a very nice thing. The optimal mechanism is always deterministic, but in multi-parameter settings, it does. Okay.
Except for some distributions where even Meyerson's is random.
No, there is always a way to do Meyerson's without randomizing.
But then you disanonymize.
Yes, you make it asymmetric. Correct. Yeah. So that's that's why I used to say that there is a way to do the single parameter mechanism optimally deterministically. Okay, yeah. Okay, so what does a randomized mechanism look like in a multi-parameter setting? Okay, so deterministic mechanisms, when you have just one agent, let's just focus on one agent. That's already complicated. Deterministic mechanism is simply a price menu. Okay, so you put a price P1 for item 1, P2 for item 2, and this basically splits the whole turf of valuations into some regions where item 1 is bought, some region where item 2 is bought. Okay, what do randomized mechanisms look like? You can do two things. One thing is to say that I'll pick a price menu randomly. Okay, that doesn't do well, of course, because if that does well, then one of the price menu should do well. Okay, so what does well is actually price menu over randomized allocations, okay, which we call lotteries. So instead of saying that you can just pick item 1 at price P1, just pick item 2 at price P2, you can also put these kinds of things in the menu, where if you pay me price P, I'll give you item 1 with probability Q1, item 2 with probability Q2. Okay, so you should be willing to risk it, just like how you do in Priceline, right? For cheap flights, you do not know which flight they are going to book or which hotel they are going to book. You pay the price. After that, it will tell you which hotel you got booked or which price you got booked. Okay. So the assumption is that the agents are risk neutral. I definitely need this, which means that I'm going to calculate the expected utility when he buys his lottery as Q1 times V1 plus Q2 times V2 minus P. Okay. Okay. So what have we done by adding this lottery? You basically have created a new market segment. Okay. Though a few of those guys who are buying item 1 and item 2 earlier will now move to this lottery. Okay. Then there's those guys who buy item 2, those guys who buy item 1. So you better segmented the market by doing this, and one will expect that if you can do this sophisticated market segmentation, you'll get better revenue. Okay, and that's exactly what's happening. And the thing is, this happens for even very simple settings. Let's look at one agent, 2 items, and IAD uniformly distributed between 5 and 6. This is from Thanos-Willis. And in a deterministic mechanism, the optimal thing to do is put a price, and it turns out to be same price for both items. And if you put these two prices and also add a lottery at just 4 cents below the price of these 2 items, then what will happen is this new segment will come up, and these people who are buying these items earlier will now switch to the lottery, which is a loss for you because the lottery is selling at a lesser price. Okay, these guys are paying P star, now they are paying something strictly less than P star, but the gain is that there is a new segment which was not able to buy anything before, and they are now able to buy the lottery because its price somewhat lower. And it turns out that the gain outweighs the loss, and you can get a factor 1.1 improvement. Okay, so this begs the question, so what happens in general, right? Can I keep on adding lotteries like this and keep on segmenting the space, right? This is one segment, you can keep on, and you can add infinitely many lotteries and segment the turf so nicely that does it give infinite improvement. Okay, by how much can randomization increase revenue? The first attempt would be to just go back to what we did for deterministic mechanisms. Okay, so what I said was, you break this item into 4 representatives. He was a multi-parameter agent, these guys are single parameter. Competition has increased, and therefore revenue has increased. Okay, that's what we argued for the deterministic setting. The same thing should go through here also, right? Roughly the competition has increased here also, so you should get more revenue, and that's what we thought for a long time. Okay, none of the examples we had basically broke this, and we were kind of shocked when we constructed an example where, in spite of the competition, the single parameter mechanism's optimal revenue is strictly smaller than the randomized optimal mechanism's revenue in the multi-parameter settings. Okay, and again this happens for a very simple setting, one agent, 2 IAD items. The distribution is so-called equal revenue distribution, which means the probability that your value exceeds x is exactly 1 by x, and I'm going to truncate it at n. What is the optimal single parameter mechanism's revenue? Okay, what is the mechanism first? It's a one item auction, right? There are 2 agents with these values, and it's a one item auction. And even if you relax the constraint, I'm saying that you can sell 2 items instead, right? You can serve both agents. You can get at most revenue of 1 from each agent, because for any price P you set, he'll buy it with probability 1 by P, and this 1 plus 1 is 2, at most 2 you can get in single parameter setting. But here is a lottery menu in the multi-parameter setting. Okay, 3 lotteries in the menu. The first lottery is what most agents prefer, okay, because it has a small price of 2.5. The second and the third lotteries are meant for people who are very crazy about one of the items. Okay, so this is how the turf looks like now. Most of the people will buy the lottery here, this is region 1. there are some people who have very large value for item 1, so they go to region 2 and they are ready to pay a price of 3n by 8. N could be huge, but there's a small set who does this. Similarly for our item 2, and this lottery menu gets a revenue of 2.277, which is more than 2. Okay, so there is a factor 1.13 gap between the optimal single parameter mechanism and the optimal randomized mechanism. Okay, but thankfully this doesn't scale more, so we are able to show that the optimal single parameter mechanism is at least half of the optimal randomized mechanism. Okay, this is joint work with Shruti Chawla and David Malik. And here is the proof. Okay. So the optimal randomized mechanisms, I don't know how it looks like. It could be some menu. It could even have infinitely many lotteries in the menu. So take that menu. Okay, I'm going to call this LMP, multi-parameter MP. It will have several lotteries, and one such lottery is general lottery is Q1, Q2, P. Okay, you'll get item 1 with probability Q1, item 2 with probability Q2, and P. This basically generalizes to any number of items, but I'm going to focus on just 2 items. And given this lottery, I'm going to construct a mechanism in the single parameter setting, okay, that has good revenue, okay, that's comparable to this. That's what I'm going to do. Here is the mechanism for single parameter settings. So remember, in single parameter settings we have broken this one agent into 2 representatives, right? So now I need to tell what each representative gets, and here's what I'm going to do. For each lottery here, I'm going to create one lottery and put it in the set LSP1, another lottery and put it in the set LSP2, meant for these 2 representatives. So if this lottery says, you know, I'll give you item 1 with probability Q1, I'll go to representative 1 and say I'll give you your favorite item. He's interested only in one item, right? The representatives each are interested only in one item. I'll give you your favorite item with probability Q1, and Q2, the item 2 you're anyway not interested, so I'll slash the price from P to P minus Q2 V2. Okay, so this can be done only after people reveal their values. And similarly for agent 2 I do this. Okay, and what's special about this lottery menu? What's special is that if this agent decides that this lottery was the best lottery for him, L, then the corresponding single parameter agents both will buy these 2 lotteries because the utility is preserved, right? The utility here was Q1 V1 plus Q2 V2 minus P. Is the same utility here. It's Q1 V1 minus this price P minus Q2 V2, which is the same. Okay, so whatever original agent chooses, this guy also chooses. See, that much is clear. So what I want to show is that this mechanism revenue is good. Okay, MSP. So what is its revenue? Consider any value V1 comma V2, and let's focus on the case where V1 is at least V2. And the revenue is of course the revenue you get from LSP1 plus the revenue you get from LSP2, which is of course at least the revenue you get from the first lottery menu. And what is that? That's exactly the price, right? He buys the lottery, so you get a revenue of the price, which is P minus Q2 V2. Okay, this is still less than P. Okay. In the original setting you got a revenue of P, here you got P minus Q2 V2, so who knows, right? This could be very small. And even if you add this revenue, it's again P minus Q2 V2, so you have 2P minus Q1 V1 minus Q2 V2. I don't know what is that, right? How does it compare to P? But the idea is that this Q2 V2 is at most V2, right? Q2 is smaller than 1, is a unit demand setting, and this is the revenue of the second price auction in the single parameter setting, right? So V1 is greater than V2, and Vikray's auction will get you V2. So this is the revenue of the second price auction in the single parameter setting. So what this guy falls short of is bounded by at most Vikray's revenue. So what I've showed now is that for any lottery menu you give me, its revenue is upper bounded by this single parameter mechanism which I constructed and the second price auction, and this is at most twice the original revenue. Okay, so that's it, and hereafter you can go through the whole story. So there we said that the deterministic mechanism, optimal deterministic mechanism in multi-parameter setting has a 2 approximation. Here it becomes a 4 approximation because you lose another factor 2. Okay, so it's the same posted price mechanism can approximate the optimal randomized mechanism to a factor 4. So that is all I'll say about randomized mechanism. Okay. So the next thing I want to talk about is, you know, what happens if you go beyond independence, right? Particularly independence seems unrealistic in unit demand settings, right? Unit demand means you are basically substitutes, right? I said hotel as an example, you know how it's very unrealistic that you have completely independent values for different hotels. On the other hand, if you allow for arbitrary correlations, Patrick Breest, Sushi Chawla, Bobby Kleinberg and Matt Weinberg show that you can get unbounded gaps between deterministic and randomized mechanisms. Okay. So what happens is that they construct these wicked distributions for which you can construct one lottery menu for every point in the support of the distribution. So you can construct a huge support and then you can keep on increasing revenue through this. The funny thing is this happens even for two items, okay, one agent, two items, that's the simplest setting. One item you can't do any randomized mechanism for. So arbitrary correlations are not allowed. So then what is a good model of correlation for substitutes? Okay. So this is something I'm interested in, and one model which we came up with, this work, was this what we called as common base value correlation. Okay. So because these items are all substitutes, right, say 3 hotels, what is the functionality served by a hotel? It gives you accommodation. So let's say that people have some common value for accommodation, and after that each hotel has its own specialty. Maybe Edgewater is close to a beach, Hilton has a good swimming pool, and maybe Wi-Fi is good at Holiday Inn, and maybe you have separate additional values for these things. And what we say is that there is a common base value V0 for getting served, and then additionally there is a Vi for each specialty. These Vi's are all independent, V0 is independent, but this is how they are correlated. Okay, this is a common base value correlation. So this guy is a business traveler and he cares about Wi-Fi. This guy is a vacationer, maybe he cares more about beach. But with this kind of correlation, right, mild correlation, but suit substitutes, you can prove that the optimal randomized mechanism's revenue is only within a factor 8 of the optimal deterministic. Same posted prices will give you a factor 8 constant factor approximation. So what are other forms of correlation which you can tackle? So that's another open question, but you can't tackle arbitrary correlations. So I'll leave beyond independence question there. So the next question is beyond unit demand. Okay, unit demand was also very crucial in doing this. For example, I said the Q2 V2 was lost, and in general it's going to be sum over j not equal to I star, or the biggest one of Qj Vj, unless all these Qj's sum to 1, right, you can't bound, and that will give you a factor k instead of factor 2 I said. So you can't go beyond unit demand with the same approach. So what can you tell about additive valuations? Right? There are other things, submodular valuation, other things, but we don't even know how to do additive. Okay. Again, the same story for additive valuations. Sergio Hart and Noam Nissan show that the gap between randomized and deterministic is unbounded, and they show that if the distributions are independent, you can get an order of log square n approximation. And this was later improved by Shinyi Lee and Andrew Chichi Yao. They give a order of log n approximation, improve the order of log square n, and still a constant factor is open. Okay, if you give a constant factor, then this will make the story exactly the same as the unit demand story. The same unbounded gap with correlation, same constant factor with independence. So this is open. Okay, so that's the story for additive valuations, and of course beyond additive nobody knows what's going to happen. So all these are interesting open questions. I'm sure there's going to have intense activity in the next few years. Then what about combinatorial feasibility constraints, right? Instead of these simple constraints, the matching constraint was just an intersection of partition matroids. What happens if you go to general matroids? This I already mentioned. This Bobby Kleinberg and Matt Weinberg showed that they developed profit inequalities for matroidal feasibility constraints, give the same factor 2, but these thresholds are adaptive. Okay. So so what are the open questions? There are several open questions, but I'm going to just focus on things which are directly related to the talk. Okay, so one is this unit demand settings. Okay, there is no need to go through this reduction to single parameter settings and go after that. Okay, that if you go through that, you can't do anything better than 2 here, anything better than 4 here. That's the end of the idea. Okay, the end, you can't extract more than that. So can you do better than 2? Okay, in fact the PTAS is open, but even anything slightly better than 2, even 1.9 is interesting to me because it's going to be a new idea. Okay, same thing for randomized. And for additive valuations, constant factor itself is open as I said, but again PTAS is also open, and the gap between randomized and deterministic is open. Okay, because this p-task could be through a randomized mechanism. Who knows? Matroid profit inequalities, again I already mentioned. Can you do it with non-adaptive thresholds? And the other thing is profit inequalities for correlated distributions. Okay, so one might think that correlated distributions are leaking more information. Therefore, profit inequality should do well. You can put thresholds and do well, but there are examples where it performs as bad as possible. So for arbitrary correlations you can't tackle. So for what kinds of correlations can you give profit inequalities which give constant factor approximations? So these are the things which are directly related to the talk. Okay. So that's it. Yeah. Thanks for listening.
More questions or comments? So as you know, this in single parameter setting, one can also handle case when the distributions are not regular, so virtual valuations are not increasing. Is that also true in your?
Yes, because I can look at and virtual values. Those are my random variables now. Just apply profit inequalities on and virtual values. That's it. Only thing is you have to be careful about. So when you're ironing virtual values, these guys have some. So how will you invert the function, right? I'm going to so I'll put a threshold on virtual values, means I'm going to invert it. But how will you invert when there is a flat region? You should invert it either using this end or that end. So you can never change the probability of allocation in an ironed region. You should not pick a price in between. Okay, as long as you do that, then you're good. So that's all there is to that.
And if I ask, what are the profit inequalities?
Profit inequalities is basically this. So you have these n random variables. A profit can see through all these random variables ahead of time and picks the biggest one. And you as a gambler are competing with this profit. You don't see the future, but still, you are saying that I'll do at least half as well as the profit. So that's the profit inequality. This is originating due to Krengel, Schuchesten and Garling. They said that the best stopping rule can give you a half approximation, but these best stopping rules could be complicated. What Samuel Kahn showed is that the simple threshold stopping rules are already good. They'll give you the same half approximation and the half is tight. Very simple examples.
So this profit inequality you showed with 1 over 1 minus 1 over root k, something like that.
Right.
Under which conditions is
This is
that
a k item
possible?
profit inequality, which means that the gambler can choose k random variables, any k he wants. Okay. So the original setting was that once you choose, you stop, right? You don't see anything the next day. Here you stop after the kth thing you choose.
Okay. And you set that, just preset the thresholds.
Yes.
You can do within that factor of the maximum over all choices of k.
Yes. Right. So if you knew everything ahead of time, you will pick the top k. Right?
Yes.
No? Thank Balu again.